So we would like to give the statement of the Hahn Banach theorem that looks really like an awkward kind of mystic statement, and we would like to just also mention the usual way that the Hahn Banach theorem is used. I mean, there are certainly many cases where we want the more general statement, but especially when we don't deal with fancier topologies, there is a much more straightforward consequence of the Hahn Banach theorem, which is usually what shows up in simple applications to the theory of normed linear spaces or Banach spaces. When one delves into the weak topologies or the weak star topologies, then of course the more general version is needed in terms of the separation theorem. But in any case, let's give the statement of the theorem. So we start with a linear space. So let X be a linear space over the real numbers. And P from X to R, what is known as a sublinear function. I, a function that satisfies two conditions. First of all, it sends the sum of two things to a number which is less than or equal to the sum of the images. And secondly, it behaves very nicely with respect to positive numbers, to scaling with positive numbers. So P of lambda x is equal to lambda times P of x for any x in x, and lambda in R with lambda greater than or equal to 0. So suppose that we have such a function, and we're going to mention in a second what kind of functions we expect that satisfy such properties. Suppose that Y is a linear subspace of X, and phi from Y to R, a linear map dominated by P, such that phi of X is less than or equal to P of X for every X in Y. Then there exists an extension of phi on all of X, i.e. a linear map let's call this psi from X to R, such that, okay, the first property just says that it's an extension, so y of x is equal to phi of x for every x in y in the original subspace. But more importantly, y of x continues to satisfy the property that it's dominated by p of x for every x in x. The fact that there exists a linear extension to phi is what we usually call in mathematics abstract nonsense. So, and I'm going to say in a second what that means. The most important part here is that it keeps satisfying the condition that phi satisfied. Okay, so that's the Hahn Banach theorem. And part of the reason why it's given in this quite strange, almost awkward manner is because its proof is very, very simple. Not easy if you haven't seen it before, if you haven't seen such an argument before, but it's very, very simple based on the conditions that we have here. So let's clarify a few things. So first of all, this is more interesting in infinite dimensional linear spaces. And when dealing with infinite dimensional linear spaces, it's a good idea to know the notion of a Hamel basis. So a Hamel basis, so if X is a possibly infinite dimensional linear space, then a Hamel basis for X is a set X abate for A in A, so that each element of X can be expressed in a unique way as a linear combination of finitely many of the elements of X sub A in A. So in other words, a Hamel base is really a substitute for a basis in the case of finite dimensions. And it's the most natural substitute. What is not clear is that any linear space, any vector space has such a basis. But this is exactly a consequence of what I called a moment ago abstract nonsense. So it's not nonsense, of course. It's what is known as Zorn's lemma, which is one of the main building blocks of modern set theory. It's equivalent to the notorious axiom of choice. And this pretty much, if you use a Hamel basis, then you can easily show that any map has an extension. So you can always get this part. Okay, so this part is not the hard part. That's why I said every map has an extension, and it shouldn't be considered as a big victory that we can achieve something like that. What the important part is that this is going to be dominated by this sublinear function. So you can find an extension that keeps satisfying this nice condition. And what I would like to tell you here is that if, for example, we have a Banach space, then the usual situation in which we apply something like this is we take a subspace Y. It doesn't even have to be closed. And then we take a linear functional from Y to R, which is linear and continuous. And the fact that it's continuous means that W star of Y, this is less than or equal to the norm of R functional times the norm of Y. So basically what we can do now is consider pi of x to be the norm of W star times x. And this can be shown to be a sublinear function. So what this tells you is that you have a linear map that satisfies this condition, pretty much. And the Hahn Banach theorem implies that you can find, and this condition can be thought of in terms of a sublinear function. And now the Hahn Banach theorem tells you that you can find an extension of this linear map to the whole Banach space that still satisfies this condition, which means that you can find, so there exists U star, let's say, from X to R, such that U star of Y is equal to W star of Y for any Y in Y, for any Y in the subspace. And in particular, and here you can play a little game with the absolute values and pretty much show that this will be true for any x in X, which means that you can extend your linear functional to the whole Banach space without increasing its norm. So it's automatically continuous because it satisfies this. And not only that, but the norm doesn't increase. So the main corollary, which is the standard way of using the Hahn Banach theorem at a more elementary level, if you like, is that if X is a Banach space, actually it can be a norm linear space. So if X is a norm linear space, Y a subspace of X and Y star from Y to R a bounded linear map, then there exists X star from X to R, extending Y star with the norm of X star being equal to the norm of Y star. It's pretty much one of the most important ways that we use the Hahn Banach theorem. And that's all I had to say about this. Thank you so much for watching.